Hello everyone, welcome to this lecture video tutorial in the mathematics of the modern world. Enjoy learning. Hello everyone, welcome back. In this lecture video tutorial, we will be discussing chapter 2 entitled Sets and Functions as reflected in the course outline of this subject, mathematics in the modern world. So as you can see here, after watching this whole lecture video, uh, the students are expected to understand the idea or the general notion or concept of a set, set operations, relations, and functions. So with respect to the concept of a set, there are what you call this one several definitions that will come after, like role and roster method, empty and universal sets, subsets and equality, finite and infinite sets, equivalent sets, cardinality of a set, Venn diagram, and so on and so forth, that will excite you and me as you watch this whole lecture video, that is by of course by studying online. Students are also expected to solve word problems by representing sets using Venn diagram. um, these are, some of the interesting knowledge or ideas to look into as you watch this whole lecture video. So without further delay, let's start lesson number 1. For our first definition, we will define the concept of a set. And please do remember that this word set is very important in the whole chapter, of chapter 1. Okay, uh, because some definitions that will come afterwards will rely on this keyword, the keyword set. Okay, so let's write our first definition. As you can see here, we'll write a text. I will put it here. Okay, and then I will write definition. Sorry, definition 1. No, a set is a well-defined collection of objects. Okay, so let's expand this a little more, and then let's have a color black. Okay, so as you can see here, in our first definition, a set is a well-defined collection of objects. So what does this definition mean? Okay, the keyword here is the word, this one. Let's have a color blue. Well defined. Okay, so what do we actually mean by the word set. Do we have to just collect any objects? Okay, so if I collect that one, and then after collecting those objects, and you will put it in a basket, okay, then that collection is now already what we called a set. So as you can see here, there is a word here. The word will define that will add up to the notion of the or the concept of a set. What does this word mean? If you look at your, what they call this one, if you look at your dictionary, uh, Merriam dictionary, okay, it says here that this word means that uh, this word means is I will write here, having clearly uh, distinguishable features or feature, okay, or feature or features, okay, or the other meaning is uh, clearly stated or describe okay. So if you look at the meaning of the word well defined, uh, when you say a set, it is not just like collecting an object, okay. There must be something that makes it more clear, meaning distinguishable features, okay. It is clearly stated, or as you can see here, describe, okay. So let's have an example that will enlighten us. Let's have an example. Let's have an example that we illustration. Let's uh, say illustration, okay. So for example, uh, suppose I have a basket. Let's search for something like a basket, okay, a basket here. Let's have, where is that example, this one, okay. Let's have a basket here. Let's make it big enough, okay. Let's have a basket here, and we will denote our basket, this first basket, we will denote this as basket A. This one is basket B, and this the last one is basket C, okay. So this basket here, uh, we will put an object uh, like this basket is a collection of fruits. Let's say this is fruits, okay, collection of fruits. This one is fruits, and this one is animals, and this one is let's say flowers or let's say cars. Okay, so when you have an object, okay, let's say for example we have apple. Okay, if you have an apple, let's search an apple here. Apple, let's have an apple here. Let's say this one. I like this color. Okay, and let's try to resize this as this one. Okay, let's put it here. Okay, when you have an apple, as you can see here, this object, okay, it says here that a set is a well-defined collection of objects. Well-defined collection, and you can see in the meaning of the word well-defined is having clearly distinguishable features. Distinguishable features. Okay, so meaning to say clearly stated or described. When you have an apple, as you can see here, then you can distinguish, you can clearly identify the object, that this apple here belongs to this collection, this basket here. Okay, uh, this apple belongs here. Okay, it doesn't belong to this collection, um, this basket B, because apple is not an animal. Okay, apple is not a car. Okay, so meaning to say, if you have an object, then you can clearly identify that object, uh, if where to put that object in a certain basket. Okay, so that's the meaning of a set. So the question now is there a collection which is not well defined? Meaning to say, is there an object, or is there a collection where if you have an object, this kind of object, uh, you cannot identify where that object belongs to. You cannot distinguish. You cannot distinguish the object if that given object belongs to a given set. Is there that kind of collection? Okay, so okay, another, let's before I will answer that, let's have another uh, image here. Let's say we have giraffe, or let's say tiger. We have a tiger. Okay, let's say this one. So, okay, let's resize this. Okay, we know that this picture here is not a car. This is not also a fruit. Okay, but this is an animal. Okay, so this picture here, this object here, belongs to set B. Okay, and we can clearly identify that this animal, the tiger, is clearly an animal. Of course, we cannot argue. We cannot argue that this is that the tiger is not an animal. Okay, all of us can identify that the tiger is an animal. Okay, let's have another image, like a car, for example. This is of course this is obvious. Okay, if you have this one, okay, mm, okay, this one, uh, this object, which is, I don't know what kind of car is this, what model. We can clearly identify that this object is not an animal. This is not also fruit. Okay, this is not an insect. Okay, we can clearly identify that this object is a car, so we can put the car in the basket C. That's basically the meaning of a set. So let's go back to my question before. Is there a collection of object which is not well defined? So the question here is, it's a black Q. Is there a collection of objects which is not well defined? Okay, so the answer is of course yes. Okay, so let's have an illustration here. uh, illustration illustration so let's have this uh, collection of sorry, let's have another color. Let's say we have a magenta. Collection of, let's say this one, beautiful ladies. Okay, let's have another collection of tall trees. Okay, let's have one more collection of um, kind kind person. Okay, okay, let's add one more collection of uh, big buildings. Okay, so this collection here are examples of collection which are not well defined. Okay, so for example, let's have a basket. Let's try to illustrate this in a more uh, beautiful illustration. Where is that? Okay, this one. Okay, I'm sorry, we have, as you can see here, uh, I have 4 collections but I have 3 baskets. Anyway, uh, for example, this collection here, uh, let's call this collection as, sorry, uh, let's try blue. This is example, this is, we denote this as, we use ABC. Let's try Q, and this one R, this is S, and this is T. We will denote that collection as Q, R, S, and T. So let's have, okay, let me draw a basket here, another basket, this one, sorry. Okay, suppose we have a basket here, so we will denote This one as Q, R, S, and T. Okay. Example, we have beautiful ladies. Beautiful ladies. Let's search here. Let's say, mm, let's say, Aramina. 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 Or no, not Aramina. Let's say Angel Luxine. Angel Luxine. Okay. Let's try to search a lady here or a girl. What happened? It's loading. I'm sorry for that one. Let's say, for example, we have Angel Luxine. Okay. So it says, can you tell me if Angel Luxine is beautiful or not? Okay. Is that something? Can we look at the definition of the word well defined? Okay. It says there that, okay, we have no image because it says it's Creative Commons. Okay. Anyway, suppose we have Angeloxine. Okay. So it says here that the word will define says that it is clearly distinguishable, having clearly distinguishable, or clearly stated or described. Okay. So meaning to say, when you have this kind of collection, this collection is not well defined. Because if you have, for example, an object like angeloxine, then example in a whole class, uh, when I ask which of you says that angeloxine is beautiful, then can you uh, assure me that uh, all of you will say that angeloxine is beautiful? Okay, so meaning to say, uh, since most of you or maybe half of you will not agree with me that angeloxine is beautiful, then we cannot put angeloxine in the basket queue. Okay, because the word set says that it is clearly distinguishable features, and unlike when you have a carabao, then we can say that if you have an object of a carabao, then we can say that okay, that's a carabao. We cannot say, oh, that's a fish, or that's a flower, you know. Can you uh, argue with me that this object here is a flower? Okay, is this a car? Is this a tree? Okay, so that's uh, the what do you call this one, the meaning of the word set. Okay, I hope you have now an idea that what do we mean by the word set. So it is clearly the word set is there is a word here uh, that adjoined to the word collection. Okay, or the phrase collection of objects. Okay, the word will define. Okay, this is very important word that will help us to identify that the given collection is really a set. Okay, then if you ask me if there what do you call a set in which uh, like the example here, okay, what do you call this kind of set Okay, if you read some books, you can read the word fuzzy sets. This examples here are example of fuzzy sets. Okay, so uh, another illustration, just like this second example, like collection of tall trees, we cannot clearly identify or distinguish that that tree is tall. What do you mean by tallness? Okay, is 2 meters tall enough? Is a 10-meter tree tall enough? So that's very hard to distinguish. Can you distinguish a kind person? Okay, so maybe for you that person is kind, but to the other he is unkind or she is unkind. Can you distinguish a big buildings? Okay, this building is big because it has 2 stories, or this is big enough because it has 20 stories. Okay, so that's clearly vague or not clear. So as you can see here, I uh, discuss the notion of the set clearly. Okay, so I hope that you clearly understand the meaning of the word set. And notice here there are some notations that I'm going to explain also here. uh, Notations, when this object uh, belongs to this basket, there is a notation that we are going uh, to use. Okay, so let's have here notation. Let's have other color or this black one. Let's have a notation. Okay, this notation example, we have an apple. This notation, that one, uh, this means that read as element. Okay, apple is an element of the set A. Okay, and we will use the capital letters of the English alphabet, this one, as a notation or symbol for a set. Okay, A B C D up to Z, and we exclude the letter U later on. I will explain that. So this read as this notation element. And if you will see a notation like this, uh, we know that apple is not an animal, so this notation is read as not an element. Okay, so I hope you are very I hope you understand this notation. Okay, so uh, that's for our first definition. Okay, so for the second definition, uh, for our second definition, we will be discussing uh, the 2 ways. Okay, 2 ways. uh, okay, I'm sorry, that's 2 methods or ways. 2 methods, let's put here, 2 methods on in describing two methods in describing sets. Okay, so as you can see here, the first one, okay, first one is the rule method. Okay, rule method. And the second one, I will leave a blank space here, is the roster method. Roster method. Okay. In other books, this is defined as the other term for this word is set builder. Set builder notation. And the other term for the roster is enumeration method. Enumeration method, or maybe I forgot the other one. Okay, so what's the meaning of the rule method? For the rule method, the definition is something like this. In this method, we use a phrase. Okay, we use a phrase to describe the elements of a set, agreeing that only those objects having the property described are elements of the set. Okay, the description is enclosed by a pair of set braces. Okay, sorry, these braces. Okay, so before I will give an example, I will define the notation for the roster method first. In this method, we list or enumerate the elements of a set, and then two distinct elements of a set are separated by a comma, and the elements are also enclosed by a pair of set braces. This one. Okay, so let's have an example to illustrate these two methods. Okay, these are the usual ways on how to describe a set. If you have another, then that's not the usual method. Okay, so let's have an example. Okay, before I go back to that definition, let's say color blue. Examples. Consider the uh, following sets. Okay, say for example, we will denote our set to be, as I've told you before, that we will use the capital letters as the notation for a set, and then the elements of the set are small case, okay, letters. So let's say the set of natural numbers, or in some other books this is called uh, counting numbers. Okay, letter B, our set B, the set of let's say the set of all the set of all cities in Luzon. Say that one. Letter C, the set of all distinct letters of the word say beautiful. Okay, the set of all letters in the say English alphabet. Letter E, the set of all even the set of all positive even numbers less than let's say 17. Letter EF, the set of all tigers. Let's say all set of all natural numbers, set of all tigers having wings. Okay, so these are, yeah, let's say we have another set G. Let's say the set of all uh, the set of all odd numbers or odd numbers uh, greater than sorry greater than uh, 3 but not less than 16. Okay, let's say that one. Okay, so these examples here are not the usual way on how to write a set. Okay, these are the only two methods or way on how to write or to describe a set. Okay, we have the rule method and the roster method. Before I forget, let me correct or let me add something here. In some books, this is what we call tabulation method. Tabular method, sorry, it's tabular method. Okay, tabular. Okay, tabular method. Okay, in some other books it says here that if you are going to use I will discuss first this rule method. This is this word definition here: roster method or enumeration method or tabular method. I will discuss this first because this is easy to understand. In this method, we list or enumerate the elements. So the keyword here is to list or enumerate the elements. Okay, the object of a set are called elements. Okay, so in apple it's an element. Okay, and then after listing two distinct objects, see here, two distinct objects, okay, of a set are separated by a comma. Okay, and then the elements, so if you have apple, banana, grapes, so you have to put a comma after apple, you have to put a comma after banana, you have to put a comma after grapes, and then it says here that the elements are enclosed. No, they are enclosed. Elements are enclosed by a pair of set braces. Okay, so for example, for letter A, have a green one or black or green. Okay. So for example, letter A, if we will use the roster method, okay, roster method. It says here using roster method, what we will get here is our A is natural numbers or counting numbers. So we know that when we count, we will start at 1. Okay, not by 0, of course. You cannot say that if you you will start 0 1 2 3. No, you cannot do that. When you count something, then you will say this is 1 2 3 4. Okay, so this 1 comma 2 comma 3 comma 4, and so on and so forth. Okay, so as you can see here, the object is separated by a comma. Okay, and since there are uh, infinite or counting numbers, we cannot list all of them. We write this notation, 3 dots. Okay, okay, so and for letter B, for the set B, so Luzon, like let's say Pampanga, is Pampanga, or Quezon City. List all the cities we have. First we have Quezon City. What other city? Manila City, Manila City, uh, and so on and so forth. Okay, but this is finite. Okay, I don't know, uh, I can't memorize all the cities in Luzon, so I will leave it a blank here. I don't know how many. Okay, you can search in the Google if how many cities are there in Luzon. Okay, but this is a finite set, meaning say you can count all of them, you can list them. Okay, for the set C, uh, and notice also it is enclosed by a pair of braces, this one. Okay, okay, sorry, pair of braces. Okay, we have a pair. Letter C, the set of all distinct letters of the word beautiful. So distinct letters, so you are going to write the distinct letters. We have B, E, A, U, T, I, F. U is repeated, so we will not write the letter U. Okay, since it says that we are going to write all the distinct letters of the word. Okay, for set D, we have the set of all letters in the English alphabet. So we have A, B, C, D, and so on up to X, Y, Z. So the rule here to write a set, if there are more than 10 objects, then you can use these 3 dots. Okay, but if the object, the elements of the set are less than 10, so you have to write them all. Okay, if it is infinite, write the first few 5 or 6 terms, and then use dot. Okay, so that's basically how you are going to write the elements of the set using roster method. Let's continue. We have set E, the set of all positive even numbers less than 10. Positive, says here positive. So even numbers less than 17. So we have 2, 4, 6, 8, 10, 12, 14, 16. Okay, so since 18 is not less than 17. Another F, the set of all tigers having wings. What's this? Did you see a tiger having wings? Of course we cannot see a tiger that have wings. Okay, so this set is empty. We cannot find, there is no object in set F. We cannot find a tiger that have wings. Okay, so no object here. So set G, the set of all odd numbers greater than 3 but not less than 16. Okay, so greater than 3. Is 3 greater than 3? Of course not, so we will start at 5 odd numbers. Okay, 5, 7, 9, 11, 13, 15. And the next odd number is 17, but it says here but not less than. Okay, but not less than 16. Okay, so the set of all odd numbers greater than 3 but not less than 16. Okay, so that's how you are going to use the roster method. So what will happen if you use uh, rule method or set builder notation? Okay, so let's recall the definition. It says here, in this method we use a phrase to describe the elements of a set, agreeing that only those objects. So we use here a phrase, let's say color red, a phrase to describe the elements of the set. We know that a phrase is something that don't have a what they call this one. Okay, this is not a punctuation mark. Okay, anyway, uh, agreeing only those objects having the property described are elements of the set. The description is enclosed by the same as the roster method. Okay, so we will create a phrase to describe the elements of the set. Okay, so be careful in describing. Okay, so let's start letter the set A. Okay, it says here the set of all natural numbers. Okay, set of all natural numbers. So usually if you, let's say, the color red, it says here that it is the same as the roster method. You have to enclose in a pair of set braces. Usually in the books, in the mathematics books, this is universal in writing the rule method of the set. So the set, this one, the set of all x, says that x is an or a, and then we write the phrase here. Okay, we write the phrase here and then we enclose. Okay, so for example, since it is a phrase, let's practice on how to write a phrase. The set of all natural numbers. Okay, so it's the set of all x is that x is it an or a? It says here natural. We have a consonant. Okay, n is a consonant. There is a difference between a vowel and a consonant. Yeah, so you have to recall your English subjects. So since it is a consonant, we will use erase this one. So for that, let's write a, this is the usual. Okay, Anyway, what should we do here? I want not to erase this. uh, Maybe I have to erase the letter here, so I will leave it as this. So I will write, let's say, another color. This is the universal way of um, of writing or describing a set using rule method. Okay. Okay, so for our A, let's have another color. So it says here that recall your example, the set of all natural numbers. So this is the set, so let's copy the set of all x, says that x is a natural number. Okay, so this is now our phrase. Okay, we have a consonant, so we partnered with okay, x is it should not be is unnatural number. No. Okay, use just recall your English subject. So why do we have to write it this way? Okay, and remember that the given is in plural form. Okay, plural with s, and then after writing it in rule method, it became singular. Okay, what will happen if you will write s here? Okay, this phrase here is grammarly incorrect. Why? So if you, let's take it back. Okay, if you look at the roster method, it says here that 1 is a natural number, 2 is a natural number, 3 is a natural, 4, 5, and so on and so forth. Our x here is a what we call a variable. Okay, this is a variable. And if you recall your algebra and trigonometry subject, or in pre-calculus or in basic calculus, when you heard the word variable, it is something that you have to replace. You can replace an object for that notation. Okay, so our x here is a variable and you can replace it. Okay, and we know that 1 is a natural number, so x, which is equal to 1, it says here 1 is, here, look at here, 1 is a natural number. That's a correct grammar. But if you put an s here and your x is, let's say another color, is 1, that one, your x is 1, can you say that 1 is a natural numbers? So as you can see here, we have a wrong grammar. Okay, when x is equal to uh, when x is equal to 2, or let's say 3 or 4, say 2 is a natural numbers, 5 is a natural numbers. So as you can see, you will have a wrong grammar. Okay, so I hope you comprehend that one. Okay, so let's erase this. This is the oops, the right way is the from the given. Okay, from the given, if you look at the given is in plural form, but if you write it in a phrase, it will become a singular form. Okay, so meaning to say, in set B, the city here will become city. When you say letters, you will have letter. Numbers, we have number. Tigers, we will become tiger. Numbers here we have will become numbers. Okay, so for letter B, the same notation, we will use this universal way of writing or describing a set. This one, the set of all x is that x is, as you can see, is it a vowel or a consonant? A consonant. Okay, it is a consonant, so therefore we will use a. Okay, so the set of all x, that x is a city uh, in Luzon. The city in Luzon. You cannot you cannot write it this way, like example number in set A. The set of all x says that x is all. You will write here, uh, you will write here all. The set of all x is that x is all natural numbers. No, you cannot write the set of all x is that x is all city. That is a very wrong grammar. Okay, let's erase that one. Okay, so do not be mistaken if you convert this uh, sentence here or phrase here. Let's, since I think I have to put a, sorry, dot here. Okay, so this is a sentence. Okay, this is a sentence, and I think I have to use a capital. In the first we have a capital letter. Okay, so for letter B, it says here the plural word for city is cities, which is used in the given, will become singular. Okay, example, your x here is Quezon. I think I have, this is wrong spelling. This is e something. Okay, Quezon City. Anyway, example, Quezon City, x is Quezon City. So the set of all x is that x. So Quezon City is a city in Luzon. Okay, that is the correct grammar. Okay, so why do we not write the word set? Okay, this one, it is because this notation here, the pair of braces, you will read this one as the set of all x such that x is a. So the set here are already converted to this symbol. Okay, so it is converted to that, to this symbol. Okay, so and this colon here, colon, can we write another, this one, this is such that. Okay, for the, okay, for the third one, the set C, this is the set of all x's that x is another, we have, is it consonant again? Consonant, where is, okay, in letter G we have consonant, 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 consonant. All are consonant. Okay, so meaning to say we cannot use an. The set of all x says that x is a letter, uh, is a letter, no, is a distinct letter of the word. Okay, sorry, is a distinct, is a distinct letter of the word beautiful. Beautiful. Okay, so a phrase doesn't have a dot. Okay, so do the same for set set D, set E, set F, and so on and so forth. Okay, so do that. A, B, C, D, E, F, G. Okay, this is do it uh, do it at home. Okay, so that's how you are going to describe a set using roster and rule method. Okay, for the next definition, we will be discussing about uh, subsets and equality. Okay, hello, I'm sorry, I have to make a correction with regards to the set G that I've discussed earlier or before. It says here the set of all odd numbers greater than 3 but not less than 16. And as you can see here, when I write it in the roster method, this is the elements of the set. I acknowledge I am that I made a mistake. Let me have a correction here. So for example, this is our set. Okay, so it says here that your x is greater than 3, and there is a word here that says but not. Okay, but not less than 16. The word but here is synonymous to the word and. Okay, this is synonymous to the word and. So it says here that your x odd numbers, your x is an odd number greater than 3 but not less than 16. Not less than, so not less than 16. Okay, so as you have noticed here, this inequality x not less than 16, you can rewrite this as x greater than or equal to 16, since it is not less than 16. Okay, and further you can write this one as x is greater than 16 is greater than or equal is less than or equal to x. Okay, so meaning our x is greater than 3 and also it is greater than 16. So this means that our set G, this is a correction, our set G is will start at 17. Okay, 19, 21, 23, 25, since it is odd, and so on. Okay, you cannot include the number 5, the odd number 5, 7, 9 to this set, because as you can see here, 7 is greater than 3, but it is not greater than 16. Okay, but initially my thought is that I should not put the word "and" here in this sentence. Okay, but anyway, since I already written it, so meaning to say that we have to solve this problem. So actually this is a correction to this set G. Okay, so this is now the correct uh, answer to the set G using the roster method. Okay, so this is the correct. Okay, this is the correct solution. Solution uh, using roster method. Roster method. Okay, so that's all. Let's proceed to uh, empty sets, the definition of empty sets and universal sets. For the third definition, we will define empty sets and universal sets. Okay, we have here empty and universal. Okay, universal sets. So this is the definition of the empty sets. An empty set is denoted by this symbol, or this symbol is the set that does not contain any element or elements. Okay, so for example, if you recall what we have discussed before, this set, okay, the set F, which is the set of all tigers having wings, is an example of an empty set. Okay, this one. Okay, so the set F, the set F below, not below, below. Okay, the set F below is an example of an empty set. Okay, for the definition of the universal set, okay, let me write it here. Definition: a universal set universal set denoted by capital letter U is the set uh, is a is a set is a set um, containing all elements included in a single discussion. Okay, so what do we mean by a universal set? Okay, so what do we mean by a universal set? So let's have an example here. It says in the definition that this set, which is denoted by capital letter U, as I've said in the previous discussion, that the this set will be denoted by a capital letters, while its elements are denoted by small case letters. Okay, so, and I've said that we reserve the symbol U, capital letter U, because it will be used in the definition of the universal set. It says here a set containing all elements in the all elements included in a single discussion, meaning to say, if you have a problem, uh, the example problem 1, the universal set is something like all the existing sets, all of those elements in that set are elements of the the set U. So that is why when you it's easy to understand the word universal. It's because the term universal is something like uh, all the elements of in a single discussion, all the elements of the set A, B, C, and so on and so forth are elements of the universal set. So for example, let's have this illustration. If you have a set A, which is the set of all students, uh, the set of all students uh, having a section code, let's say uh, code OA1A. Okay, and we have letter B here, the set of all engineering students in CMU. Let's say here in CMU. Another letter C, set C, let's say the set of all students having math, having, let's say, MMW subject in CMU. Okay, so what is the question? If you have these three sets and you can add more, the question is what is the universal set of the three sets above. Okay, uh, these three sets here are these sets. Okay, so it says in the definition of the universal is you have to create a universal set in which all these sets or the elements of these sets are elements of the set U. If there is one student that doesn't that you cannot find it in the set U, then the set U is not the universal. Okay, that's what we mean by the universal set. Okay, so for example, your U here is probably you can write as the set of all students in Central Mindanao University. The set of all students in CMU. Okay, so notice that CMU. Notice that if a student, example in the set A, if you have a student which is, let's say, Anna, she has a subject which has a section code OA1A. So Anna belongs here, but Anna also belongs to the set U because as you can see here, the set U is the set of all students in Central Mindanao University. Okay, this word here CMU is very important because probably there will be an existing code here in other university, like in CMU or in VSU or in CMU or in Palawan State University. So this is very important keyword here. uh, Notice that this set is, we can say that this is universal because this is a big, really big set. All of the elements in this set A, B, and C are elements of the set U. So remember what I said before, that if uh, there is one element in set A, B, and C that uh, doesn't belong to the set U, then this sets here, this universal set here is not anymore any universal. But if you add a set, let's say, let's have a color magenta or purple. We have set B, like this is the, you add the set of all, let's say, counting numbers. Okay, so if you add a set D, which is this set, this set here U is not anymore the universal set. It is because it says here is the set containing all elements in a single discussion. Okay, in a single discussion. Okay, um, okay, in a single discussion. So this is what we call an instant where we say that that this set are in a single discussion. Okay, if we have a 1 here, we know that this is a counting number. We know that 1 is not a student. Okay, 3 is not a student in CMU, or 5 is not a student. Probably there will be a student whose name is 3, but it's very unlikely that there will be a student whose name is 1, 2, 3, 4, and so on and so forth. Okay, so that's what we mean by a universal set. Okay, for the next definition, we will be discussing about subsets and subsets and equality. Subsets and equality. So let's discuss subsets and equality. Okay, so for this word what do we mean by a subset? Okay, so from the word itself, it says here it is a set. Okay, there is a something like an added word, which is sub. Says here set A is a subset of set B, uh, denoted by this symbol if every element of A is also an element of B. Okay, so for example, if you have just look at your previous uh, examples like this one. Here we can say that uh, set G is a subset of A. Okay, E is also a subset of A. Okay, uh, let's write it here. In the previous discussion, we have G is a subset of A. Set E is also a subset of A. Okay, because every element in E is also an element of A. Every element of G also is an element of A. E is not a subset, okay, of G, because there are elements in E which is not an element of G. Okay, G also is not an element, is a subset of E, and so on and so forth. Beautiful, the set of all distinct letters in the word beautiful, which is denoted by D, okay, is a subset of let's recall, there's that one, C. Okay, sorry, C is a subset of D. Okay, sorry, C, no, set C is a subset of D. Okay, remember that the set C is the set of all distinct letters in the word beautiful, and the set D is the set of all letters in the English alphabet. Okay, set D is not a subset of set C. So let's have a notation here. Sorry, let's have another color notation. This notation read as not a subset. Okay, and so on and so forth. Remember that the set F is always a subset of any set. The empty set is always a subset of any set. Okay, B, C, D, F, G. Okay, so let's have a note. The empty set is always a subset of any set for all set A. Okay, also A is a subset of B for all set A. Why? Because of course every element in A is also an element of B. Okay. Number 3, A is always a subset uh, of the universal set for all set A. Okay, as long as with respect to a single discussion, A is part of that given. Okay, so that's the definition of a subset. Okay, so what do we mean by equality? Okay, so it says here two sets A and B are said to be equal, denoted by this symbol if uh, A and B uh, have exactly the same elements. Okay, that is A is a subset of B, and at the same time B is a subset of A. Okay, so remember the conjunction here, and when you say equal, okay, when you say equal, which is denoted by this symbol, A and B have the same exactly elements. Okay, that's very easy to understand. Let's not have an example here because as you know, that definition is clearly understandable. Okay, for the other, let's say let's have another definition. Okay, the definition of the finite and infinite sets. Infinite sets. Okay, so before we define the the word finite and infinite, let's have this definition first. Okay, the definition of the one-to-one correspondence. Okay, this is the definition of the one-to-one one one-to-one correspondence. Okay, uh, if you are given two sets A and B, then A and B are said to be in one-to-one correspondence. Let's have a color here. One-to-one correspondence if there is an equal pairing of elements between A and B. So let's have an illustration. So as you can see here, first of all, you are given a two sets. Okay, then if you can map or you can match every element of set A and set B, and all the elements of A are equally paired with the elements of the set B, then uh, set A and B are said to be in one-to-one correspondence. So for example, if you have a set A here, which is 1 2 3 4 5 6 7, and then if you have a set B which is A B C D E F G, 1 2 3 4 5 6 7, okay, when you say there is a one-to-one correspondence, this means that example 1 is mapped to B, doesn't matter, 2 is mapped to D, 3 is mapped to C, 4 is mapped to G, or 5 is mapped to E, 6 is mapped to A, and 7 is mapped to F. So all you have to do here is to count. Then if they have the same number of elements between A and B, then basically uh, the set A and B, the given set A and B are in one-to-one correspondence. Okay, so what if you ask the question, can I pair it like this, sir, like this one? Okay, you can do that. It doesn't matter as long as uh, all the elements of this set are paired. So let's have a practical example. Let's say in a classroom there are 50 chairs, and also there are 50 students. The set A is the set of all chairs, and the set B is the set of all students, 50 students. Then the set A and B are in one-to-one correspondence, because as you can see, you can map every student to every chair in this set B. Okay, so that's basically what do we mean by a one-to-one correspondence. Okay, so let's define now what do we mean by finite sets. Okay, definition. uh, definition Finite sets: a non-empty set is said to be finite if for some fixed counting number n, it is equivalent to the set 1 2 3 and so on up to n. Okay, this means that if the given set is finite, it means that you can completely list all the elements of the set. So that's what we call the finite set. Okay, so for example, here, if you look at your previous discussion, the set B, C, D, E, F, and G are finite sets. They are finite. Okay, B, C, D, E, F, and G are no. G is not finite, as you can see. we correct ourselves before that this we have a dot here. By the way, these three dots, if I remember it correctly, these three dots here are called ellipses. Ellipses. Okay, so that's what do we mean by a finite set. If uh, a non-empty set, a non-empty set that is not finite is called an infinite set. Infinite set. So meaning to say, if you cannot list all the elements of the set, then that set is called an infinite set. Okay, so example for this example is the set A and the set G. Okay, another definition that we are going to define here is the cardinality of the set. Okay, this is basically under the finite and the infinite sets definition. Okay, the cardinality of a finite set A denoted by n of A. Some other books they write it as absolute value of A is the number of number of elements of the set A. So for example, n of A, since A is, in the previous example, A is an infinite set, then we can write the notation, this one, infinity sign. Okay, n of B, I don't know how many cities in Luzon, so I write it question mark, but actually you can count them. So just visit the Google website and search for how many cities are there in Luzon. So n of C, or this is the set of all that distinct letters in the word beautiful. So beautiful, as you can see here, beautiful, where's that? 1 2 3 4 5 6 7 8. Okay, E, let's count them. 1 2 3 4 5 6 7 8. 8 again, 4 8. Okay, so, and by the way, also the empty set is also a finite set. Okay, so n of C is 8, the set of all distinct letters in the word beautiful. D is the set of all letters in the English alphabet, which is 26. N of E, we count them before, this is also 8. N of F is 0. The set F is an empty set, so we have no elements, so we have 0. N of G is an infinite set, so that's why we write the infinity sign. So that's what we mean by cardinality of a finite set. Or you can use this notation, or you can write this as this one, or this one, or and so on. Okay, that's that's what we call uh, ha- the I guess the fifth definition or the sixth definition. Okay, for the we have another definition here, the definition of the Venn diagram. Venn diagram. Okay, Venn diagram. Okay, so a Venn diagram, this is a diagram showing the relationship relationship among sets and between elements and sets. Okay, that's what we mean by a Venn diagram. So for an illustration, let's have an illustration here. Illustration. A Venn diagram is usually will look like this. The big uh, the big rectangle will be denoted as your universal set. Okay, this is your, let's have another color. This is our universal set. So either you can write it on the top right or top left of the square, and then the, for example, if you have this set, this object, you can put a circle. Okay, it's not working. Okay, and then if you have a triangle, sorry, a triangle here, and then another, let's say an oblong. Oops. Okay, sorry. About a square. Let's have another color, another object. Let's say a square. Let's put it here. Oh, what happened? Let's extend this. What happened? And move it there. Oops. Okay, so let's erase this one and put the U here. Okay, if you have a set, this set here, let's have another color. Let's say okay, let's have this set D. Okay, and you have an object here. For example, you have your object here. You denote by small case. Let's say color blue. This one B, or A is here. Let's say A is here. Okay, and C is here. So this is an example of a Venn diagram, and we can put a description below that. I can say that uh, let's say B is an element of the universal set, but not in all given sets. Okay, or probably you can write C probably you can write C is an element of the set D, but not in A. Okay, you can also write a description that way, and there are so many other description that you can extract in this diagram. Okay, so this is basically what do we mean by a what do you call this one, a Venn diagram. Or let's have another object here. Let's say this one. Okay, so this is our set. This is, for example, this is set E. Okay, what happened? Okay, this is set E. So we can write that C is a set. C is a no set E is a subset of D, and C is an element of small letter C is an element of E. You can also write it at that way. Okay, subset because every element of E is also an element of D. Okay, so that's what we mean by a Venn diagram. So for our next lesson, we will be discussing about operations on sets. Okay, so we will be talking about the union, the intersection, the complement, set difference, Cartesian product of sets. Okay, so just wait for our next lesson. God bless everyone. Okay, for our last topic, we will be discussing about operations on sets. Okay, for the first operation, we have the definition of the union. So as you can see here, the union of two sets A and B is said to be is the set of all elements that belong to either A or B, or both A and B. So this means that if you take the union, so let's have an illustration here. Illustration. Okay, if you are going to take the union of two sets A and B, then you are going to get all the elements that belong to either A or B, or both A and B. So no repetition means to say that when you say the set is well defined, then it means that the elements of that set are distinct. Okay, so for example, if you have this set is not related to our previous examples. So for example, if you have A, which is 1 2 3 4 5 for a simple illustration, and you have set B, which is 2 4 6 10. Okay, then if another set, we have 1, 5, 8, say that set only. Then the union, for example, if you want to get the union of A and B, then all you have to do is to put all the elements A and B in this set, but uh, without repeating its elements. Okay, so 1, 2, 3, 4, 5, 6, and 10. So 2 is repeated, 4 is repeated, so uh, just put only one element in this set. Okay, uh, notice also that this is equal to B union A. Okay, so it's commutative. You just recall your algebra in your high school mathematics. Okay, another example, if you have B union C, so 1 is not repeated, 2, 4, 5, 6, 8, and 10. Okay, again, this is equal to C union B. Okay, another, if you want to get the union of A union C, then this is equivalent to 1, 2, 1, 2, 3, 4, 5, and 8. Okay, so you are not going to repeat the elements twice. Okay. That's what do we mean by a union. So for the intersection, okay, the intersection of two sets A and B is the set of all elements that belong to both A and B. So meaning to say, if if you look at this previous example, let's say this color, example, if you have a intersection B, by the way, before I forget, the notation for the union, is this symbol. Okay, for the intersection, we have this symbol. Sorry. Okay, what happened? Let's wait for the program to respond. Okay, for the intersection, it will be denoted by this symbol. Okay, so for the intersection, okay, for this example, this is our A, this is our B. So all you have to do is to get all the elements that belong to both A and B. So meaning to say those elements that are common to both A and B. So 2, 4 only. Okay, this is 2 and 4 only. As you can see here, the common is 2 and 4. Okay, how about notice also before I forgot, this is just the same as B intersection A. So the intersection and the union are commutative. Okay. How about let's say B intersection C. Okay, this is what are the common. So this is our the common is for B and C. There is no common element, so this is an empty set. Okay. Again, C intersection B is empty because the intersection operation is commutative. How about A intersection C? Okay, so is there a common? I think there is a common, which is 1, 2, 3, 4, okay, 5 is common. 1 and 5, 8. Okay, so this is what we mean by intersection. And also let me remind you that if you are going to use a Venn diagram, the Venn diagram for intersection, there are, let's have a color black. Okay, there are two possible Venn diagrams. Venn diagram for two sets A and B. Okay, so this is the possible scenario. Okay, for example, if you have this is your universal set. Okay, and this is your U here, so it could be that they intersect. Sorry, I think I have to copy. Can I copy this? Paste. Let's move this. Okay, what happened? Let's move this object. Let's wait for the program to respond. Either you have this possible scenario, okay, or this is your A, this is your B. So when you say union, then you have to shade. Can we have a nice color here, like a blue one? Blue. What happened? Okay. So you have union, then you have to shade all of them. Again, let's wait for the program to respond. Okay. since it is union, it says in the definition that you have to what they call this one, to get all the, if you look at the definition, it says there that uh, the union of two sets A and B is the set of all elements that belong to either A or B or both A and B. So meaning to say you have to shade all of them. Okay, so this is your first scenario. This is A union B. Okay, for the other scenario you can have this one. Sorry. Can I copy this? Copy, and paste. Okay, then let's move it here. Okay, let's copy this object, copy, okay, and then paste. Wait, sorry, what happened? So let's wait for the program. I guess I have to make another circle. So let's say this is our U. So let's make another circle. Let's make another. What happened? I want to have a perfect circle. Okay, so what happened? Why I cannot make a perfect circle? Anyway, I have to, this is another scenario. Okay, let's have, is this because of the internet connection? Can we copy this? No. I'm sorry that I cannot copy. So let's try again. Anyway, what happened to ink to shade? It takes a lot of time, so let's go back. Let's try another circle. Why? Sorry, I cannot make a perfect circle. I think I have to hit first. Okay, anyway. Maybe this is because of the internet connection. Okay. I cannot make a perfect circle. Okay, I think I found the right one. This one, can I delete this? Oh, delete this also. Okay, this is a perfect circle. Copy, paste. And let's move the circle here. Let's wait for the program to respond. Okay, this is the another scenario for the on how to shade the region of the two sets A and B using Venn diagram. Okay, so let's try to shade it. Let's wait for the program to respond. Okay. This is how you're going to shade the region using Venn diagram. Okay, these are the two possible scenarios on subset using Venn diagram. Okay, for the intersection, there are also two ways. Okay, for the intersection, let's see here. Same as concept of union. Okay, so for example, but the shaded region is different. Okay, so example, if you have a Venn diagram, okay, let's move this downward. Okay, and then hopefully if I can make a circle, perfect circle in just one stroke. So example, this is your set, your universal set. So if you have a common intersection point, okay, so what if you have it? Let's make a perfect circle here outside, maybe. Let's say no. Let's say again no. Oops. This is very frustrating. That one. Is that a perfect circle? Okay. Then let's copy this. Copy and then paste. Let's move the object here, left side, and then the other one, let's try it. So what if we have a comma? Okay, so let's copy this so that later we can easily make it's also may copy this one. Copy, paste. Let's wait for the program again to respond, and then let's move to the right side. Okay, what happened? Copy, paste. Okay. So sample, this is our small backward. This is a intersection B. Okay, so your description must be below the universal set. So if this is your A and this is your B, if this is your A, this is your B, then if you are going to take the intersection and the two sets are overlapping each other, all you have to do is to shade this the common. Okay, because if you look at the definition, it says that uh, the intersection is the elements, set of all elements that belong to both sets A and B. Okay, so be careful to shade. Okay, but this one, in this case, for this second case, let's have a color green. This is case 1, case 1. This is for case 2. Okay, for this second case, there is no intersection, therefore you cannot shade any region here. Okay, so that's two possible cases for the intersection. Okay, let's move this. Okay, this is the first case, case 1, and case. Notice that this is not, this diagram here is not limited to two sets only. You can extend to how many sets, but be careful what is being asked in the problem. Okay, so for example, this one. Okay, another example, if you have, for example, if you have 3 sets. Okay, if you have 3 sets, let's say you have this one. Okay, then if you have a circle, an oblong, and then if you have a triangle, and then you have a square. See this one. Okay, and if this is your universal, this is your set A, your set B, your set C, and then you are asked to shade the region of the sets A intersection, let's say B, and in this case the shaded region is this one. Okay, this portion here. So the answer for this is this one. Okay, that's a intersection B. But if you are asked, let's try to erase that one. Okay, let's say you are asked to get the example is example you are asked to get A intersection B, let's say union C. Okay, so this is just the same as in the in numbers. If you have the presence of a grouping symbols, then you have to start in that portion. Okay, this is the presence of the grouping symbols, therefore you have to evaluate this first, and then after getting the value of this, then you have to get the union. Okay, so for example, A intersection B, so we have here, since this is union, then you have to shade this region here and at the same time shade this region here. But let's try to solve this. So the answer for this one is 1, and then union, so you have this one. Okay, I'm sorry, let's try to shade. Let's wait for the program to respond. Okay. That's the answer for this question. But if this notation here will become, if this will become uh, this will become this one, if this will become intersection, what will happen is that the intersection of this set, which is C, and this set is nothing. So meaning to say the answer is empty. So you don't have to put a, you don't have to shade any part of this set, okay, if you change that one. So that's as I've illustrated a while ago, that this that the things that I've discussed uh, in the above is not limited to two sets only. You can extend to more sets, but don't forget to uh, to remember these possible cases or scenario, that if you are giving a two sets and then you are asked to get the union, then you have to shade all of them, okay. But if it is intersection, then it must be the common, okay, just like this one. Okay, for the next definition, we will be discussing about, we are almost done, um, the complement of a set. So we have the complement of a set. A is the set of all elements of the universal set U that do not belong to set A. Okay, so what does this mean? It must be that before getting the complement of a set, then you must have a universal set. You cannot get the complement without the universal. Okay, you cannot perform the complement of a set. So the notation for the complement is denoted as A prime. Okay, A prime, or some books they use A to the C. Okay, so let's have an illustration here. Let's have some example. Let's wait for the program to respond. Example. So if you have your set before, let's say let's have another example. We have 1, 3, 4, and let's say 6. So if your universal set is 1, 2, 3 up to 10, then what is A prime, or what is A to the C? It says here that it is the set of all elements in the universal set U that do not belong to set A. Do not belong. So which of the elements in the set, in the universal set, that do not belong to set A? So remember that 1 is belongs to set A, 2, 3, 4, and so on. But here 5 does not belong to set A. 6 is here, 7, 8, 9, and also 10. Okay, so if you have another set like set B, which is 3, 11, no, this, that will become the universal set. So let's try, what happened? Let's try 3, 7, 8, and 10. So our B prime here is the set of all elements in the universal set is one that do not belong to set A. So the answer is 1. 1 is not an element of B, so we have 1, 2 also. 3 is here, 4, 5, 6, 7, 8, 9. So that will be our complement. And the Venn diagram for the complement, Venn diagram. Okay, the Venn diagram for the complement, Venn diagram. We have only one case. So for example, if you have, this is your universal set. The universal set is usually denoted as the geometric figure that is associated for the universal set is the rectangle. So example, if you have this one, circle. Let's wait for the program to respond. Okay, it did not respond. Let's copy this. Okay. Paste, and then let's move it here. We have A. This is your set A. So this is your set A. The complement of the set A is the set of all elements. This is our universal, the rectangle, that do not belong to this set. So meaning to say this outside of A. So let's have a color here. So it will take time to put a color here outside of A. Let's wait for the program to respond. You have to shade all of outside of A. Okay, you have to shade what happened? Okay, so you have to shade all of this is what A prime looks like. So what happened? So this is our A prime, which is outside of A. Okay, so that's how the Venn diagram of a complement of a set A looks like. Okay, for the fourth definition of the operation, we have the set difference. The set difference A minus B, or the symbol, as you can see here, this is the notation, is the set of all elements that are in A and not in B. Okay, so let's have an example here. If you have, let's say, okay, this previous example, okay, if you look at, you can perform the difference of a set without a universal. Okay, so this is our A and B. In the previous example, your set difference is, okay, just analyze, look at this, look at the definition. The set of all elements that are in A but not in B. Okay, in A but not in B. So 1 is here, but 1 is not here, so we will write 1 here. 3 is here, but 3 is also here, so we will not write 3. 4 is here, but 4 is not here, so we include that in the set difference. 6 is here, 6 is not here, so we have 6 is also an element of A minus B. Remember that A minus, this is not equal to B minus A. Okay, the operation set difference is not commutative. Okay, to see this, let's compute B minus A. Okay, so again, this is in reverse condition. Reverse meaning to say you have to look at B first and then go to A. So is 3 an element? 3 is here, and is 3 an element of A? The answer is yes. Therefore, you will not write 3 in this set. 7 is here, 7 is not here, so we will write 7. 8 is here, 8 is not in set A, so we have to put 8 here. 10 is in set B, but 10 is not in A, so therefore we have to write. As you have noticed, the set difference A minus B and B minus A are not equal. So what does the Venn diagram of the set difference look like? So let's have the Venn diagram for set difference. Okay, so let's have, there are two cases to consider. So example, if you have, okay, so let's copy this. Let's wait again for the program to respond. Copy, paste, let's move. So we have first case, and then we have the second case. Okay, before I forget, I will have to write the notation here for A prime. This is for A prime, A prime. This is for A minus B. Okay. A minus B. Make a circle. Okay, this is what I draw is not a perfect circle. It happened. Can we draw a circle outside? Okay, we have a circle here, and then let's copy and then paste. Copy then paste. If you have a case like this, okay, that one, let's copy and then paste. Let's move this to the other side. Copy, paste. Okay, so this is your A, this is your B, A, B. Just let's go back to the definition. It says that the set of all elements that are in A and not in B. Okay? The set of all elements that are in A but not in B. So the diagram will look like this. This is A minus B. Okay, the elements that are in A but not in B. Okay, but for this case, the set of all elements that are in A but not in B. So we need to say you have to shade all this, all the objects or elements in the in the set. Okay, so how will you uh, recall or study if uh, if you are asked to get the or to shape the region using set difference? Okay, just imagine this very simple illustration. So for example, if you have if this hand here, if this my left hand, if this is your cake, so this is your set A, and then this is your set B. So when you say A minus B, so all you have to do is to overlap. Okay, overlap the set B to set A, and then the remaining one, those objects that remains, this one here, okay, is what we call the set difference. Okay, so note this is in the case 1. Notice that if the sets did not overlap like this one, so notice that when you use a minus, then this object here will, these elements here in A will remain. Okay, so that's basically what happened if you are going to use the Venn diagram of the set difference. Okay, so let's have this illustration. For example, uh, notice, let's these sets here, these are the elements of the set A and B. So let's try to put the elements here. For example, if you have one, A is 1, the common is 3. Can we put it here? 3, and then there's no other common. So 1, 3, 4, 1, 4, 6 is here. 1, 4, and 6, and 8 and 10 are 7, 8, and 10 are here. Okay, so notice in our illustration or example, the value that we get when we apply the operation set difference, it's clearly in the shaded region. Okay, clearly in the shaded region. Okay, 1, 4, 6. But for B minus A, this is this one, 7, 8, 10. Okay, so this happens because there is an intersection between A and B. Okay, for this one, if we have if you will consider the A prime, so notice that our A is 1, 2, 3, 4, and 6. 1. Okay, we don't have a 2 here, so let's let's say it again for the program to respond. We have 6 here. So notice that the complement of the set is outside of the set A. So if you are going to write the elements of the set U, we have 1, 2, 2 here, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so notice in the A prime, these elements 5. Okay, I think I is this complement. Okay, so it's a good thing that we recall. I guess I was wrong, so let's correct this. I think we also have to include number should be 2 3. No, 3 is outside. Okay, let's erase this. What happened? Okay. Erase number 3 and then color it again. Okay, so 1 2 must be an element. We have to wait for the program to respond. We have 2 is also an element here. 2 5 7 8 9 10. So 2 is the only missing elements of this set. So clearly 2 must 2 is not an element of A. Okay, so that's what happened in the diagram. Okay, you can do the same for union and intersection. Let's try it. Let's try. What if this, where is our A? Our A is 1 2 3 4 5. 1 2 3 4. Your A is there an intersection between A and B? We have 2 and 4. Okay, so 2 and 4 is here. So 2 and 4. Okay, so we have 1 2 3 4 5. Okay, and then what are the elements of the set P? Let's wait for the program to respond again. 2 4 6 10. We have 2 4 6 10. So let's look at our answer. Clearly the intersection is in the shaded region. Okay, so if you put a set C here, then you can solve that the intersection between A and C is 1 and 5. Okay, just practice. Okay, I guess we are done. We are almost done. We have Cartesian product. The last definition. We have the Cartesian product of the sets A and B is the set of ordered pairs. Okay, so the notation for the Cartesian product is A times B, and for our notation, the set descriptive notation is defined as this one. This is the set of all ordered pairs such that A is an element of A and B is an element of B. So for example, if you have set A which is 1 2 3 and your set B is AB, okay, the set containing AB, then your Cartesian product, all you have to do is, this is the set of all ordered pairs. See, notice here that A is written first, and then B comes. Okay, meaning to say the first coordinate comes from the set A, then the second coordinate comes from the set B. So from here, let's try color green. One A, 1B. So we have 1A, 1B, and then let's have another color, it's a B. 2B, 2A. We have 2A, then 2B. We use here roster method, and we know that the elements are separated by a comma. And then last one, sabi color magenta, 3A and 3B. You have 3A and then 3B. So that's those are the elements of the Cartesian product. But if you get the reverse, notice that the Cartesian product is not commutative. Okay, you will get B times A. Oh, no. But what is B times B? All you have to do when you get B times A is that to reverse is you have to interchange the coordinates. Okay, so for example, if you have, let's say, B times A, then this is A1, B1, A2, B2, A3, and B3. So they are not equal. Of course, 2, 3, and 3, 2 in the Cartesian plane, you plot those points, they are not equal. So what is B times B? So if you have B here, which is AB, and then B here, so what will happen is that this one, okay, so we have A and then AB, then this one, then okay, BA and then BB. Okay, so to make sure that you have a complete list of the elements of the Cartesian product, all you have to do is to count the number or get the cardinality of the set A and B and then multiply. So notice here the cardinality is 1, 2, 3, and this one is 1, 2. So we have 3 times 2 is 6. So the elements, we count them, there are 6. 1, 2, 3, 4, 5, 6. For this one is 2. 2 times 2 we have 4. So 1, 2, 3, 4. Okay, that's the operations on sets. So for the last topic, we will be discussing about the application of sets, about counting problems. Okay, so just wait. Hello everyone, this is our last topic about sets and sets operations. And the last topic is entitled application of sets. This is all about counting problems. So in here, I am going to give 2 examples, and then let me remind you that not all word problems can be solved using algebraic solutions. Okay, so sometimes there are problems that you will use the idea of a sets. Okay, so we have example number 1. Miss Julieta Cruz took a survey of 3 TV programs watched by the students in her class. The figures she gathered were as follows. We have here news, we have 17 students. Concerts, we have 23 students. Sports, 19. News and concerts, we have 6 students. News and sports, we have 4 students. Concerts and sports, we have 9 students. And news, concerts, and sports, we have 3 students. Okay, so the question is, the question are, as you can see here, how many students were there in the class? Okay, for this first question, is it logical to answer this question by adding all these numbers here? The answer is, of course, no. Why? Because as you can see here, if a certain student were asked if he or she watch news, then these students belong to these 17 students. However, if again that students were asked to if she watch concerts, then that student also belong to these 23 students. So she or he may be counted twice, okay, or maybe thrice, because he or she watch all the TV programs. Okay, so we need to say for letter A, it is not logical to add all these numbers here to determine if in the class this is the right number of students in the whole class. Okay, so what we will do here is the solution for here is to make a Venn diagram. So you will have a geometric figure for news, another geometric figure for sports, and another geometric figure for concerts. Okay, so we have solution. So again, for the universal set or the classroom will be denoted by the geometric figure rectangle. Okay, this is our universal set or our classroom. Okay, and then we will make a geometric figures. Let's say a circle. Okay, a circle. What happened? A circle. Sorry, I cannot make a perfect circle. Okay, that one. So you can make a square or a triangle, but that will be more troublesome in the diagram. Okay, let's use circle. Okay, what happened? Let's use 3 circles. Okay, for news, concerts, and sports. Let's try to face it that way. Okay, I guess this is enough. So this is our set N, which is our news, and then we have concerts, and then we have sports. Okay, so the first thing to attack this problem is to start with the bottom. Okay, so locate first those students that watch news, concerts, and sports, and then move upward. Okay, so it says here that there are 3 students watch news, concerts, and sports. Okay, what happened? The program is not responding, so we have 3 here. Let's try another color. Let's say violet. Okay, and then for news and sports, there are 9 students. News and sports, there are 9. So it should be here. Okay, it should be here. This shaded. If you look at the arrow, these are the students that watch news and sports, and it says there that there are 9 students. So since there are 3 students already, so we put their numbers, number 6. Okay, there are repeated students that are in here. Okay, these students watch the number 3 here, watch the 3 programs, but again these students watch also news and sports TV programs. So this is the reason why we have 9 minus 3, which is 6. Okay, so for the news and sports, we have 4 students. News, oh, what happened? Concerts and sports. Okay, I was wrong. This should be let's go back. 6 must be here. Okay, concerts and sports. Concerts and sports. What happened? Let's wait for the program to respond. This is the problem if you have a low-tech laptop. News and sports is 4. So news and sports is 4. We have 3, so the remaining is 1. Okay, and then after we have news and concerts is 6. Okay, if there are 3 already, so 6 minus 3 is 3. Okay, so for news and concerts. Okay, and sports is 19, so the remaining, this is the whole set for sports, we have 19. So 6, 9, 10, 19. So 19 minus 10 is 9. Okay, for concerts we have 23. So 23 minus 12. 23 minus 12, we have 11. 12. Okay, 23. So for news is 17. So 6, so this is 10. Okay, 10, 13, 16, 17. Okay, so as you have noticed, to answer letter A, all you have to do is to add all the numbers in this set, not these numbers. And also, just before trying to answer letter A, just read again the problem. If there are problems that they put here the number of students in the class. Okay, so for example, Ms. Julieta took a survey of the programs where programs watched by the students in her by the 100 students or by the 500 students. If that's the case, so what you will do here is you add all the numbers here, and then example, you have in the question, if you have 150 students in the class of Miss Julieta, then 150 minus these numbers. Okay, and then you put it outside. The numbers that you are the number that you are going to put outside are those students that did not watch any of the program. Okay, so meaning to say they don't have maybe they don't have TV, or that's really the case. Okay, they don't have TV. Okay, but anyway, since if we read again our the problem and we cannot see uh, any number here in the class of Miss Julieta, then meaning to say these are the only students of Miss Julieta. So to answer letter A, the answer for letter A is you have to add. Okay, you have to add, say green, all the numbers. We have 10 plus 11 plus 9 plus 3 plus 6 plus 3 no, plus 1 plus 1 plus 3. So this is 20, 30, 39, 40, 43. So there are 43 students in the class of Miss Julieta. For letter B, do not forget to write the word students. Okay, if you are asked about dogs, then write dogs. How many students build only one program? So notice here that these are the students here. Okay, let's try another color. Let's see. Okay, let's wait again for the program to respond. Let's say, okay, let's do only one program. So notice that these numbers here are those students that watch only one programs. Okay, one program. Okay, so you have to add that one. What happened? We have 10 plus 11 plus 9, which is 30 students. Okay, 30 students. For letter C, how many students viewed only 2 programs? Okay, so for this question, for letter C question, let's try another color. Let's say orange. These are the students here. This one that viewed only 2 programs. Okay, and in the center, those are the students that viewed only 3 programs. Okay, so the answer for letter C is 6 plus 3 plus 1, which is 10. So there are 10 students that viewed only 2 programs. So that's the solution. Okay, for the let's go now to the next question. At least we have 2 examples. Oh, what happened? No, let's okay, for the next question, it says here, a cartoon company is making plans for future anime movies it wishes to produce. The company has done a random survey of 900 people. The results of this survey are shown below. So as you have noticed here, unlike example number 1, the problem put a value of 900 people. In the previous example, it doesn't look that way. Okay, so be careful. I purposely put this example number 2 to have a an idea on how to solve a word problem. Okay, so there are 545 people like action sci-fi, 289 like fantasy, 147 people like both action sci-fi and fantasy. As you have noticed also here, there are only two groups of people: those people that like action sci-fi and those people that like fantasy anime. Okay, so there are two sets here that we are going to make. Unlike the example number one, there are three sets. We have news, sports, and concerts. Okay, so be careful with that one. Sometimes there are problem that you will use four sets, uh, five sets, and so on and so forth. So be careful. Okay, so uh, the question is, of the people surveyed, how many people like action sci-fi but not fantasy, like fantasy but not action sci-fi, do not like either of these types of cartoon movies? So let's again um, solve this uh, using Venn diagram. You cannot use algebraic solution. Okay, uh, the best way to solve this problem is using Venn diagram. So let's have a universal set. Okay, so this is our U, and there are only two sets. We have action sci-fi and fantasy. So let's try to make a circle. Let's say if it will work. It did not work. Okay, so meaning to say we have to make another circle. Okay, let's have another circle. I hope I can make a perfect circle. That's the problem, because we have a very poor internet connection and my laptop is running slow, so this is really a big problem. Okay, it didn't work. Let's make it again by, yes, finally. I have to copy this and then paste, copy and paste. So paste, then let's make it even or more beautiful by aligning the two circles. Let's move down, and then let's mark this is S, or action sci-fi, and then for fantasy we will use the capital letter F. Okay, so again, as I've told you in the first example, you will have to start at the bottom. Okay, start at the bottom and then move up. Okay, so here, okay, so first we have 147 like both action sci-fi and fantasy. So here 147, so let's put 147 here, 147. Okay, and then 289 people like fantasy. So fantasy 289, so 289 minus 147. So let's have a calculator. 200, calculator here, 289 minus 147, so 142, and then for the last one, we have 545 people like action sci-fi. So if there are 545 minus 147, so you will get 398. Okay, 398. 398. 398. Okay, so notice that in our question, let's look at, hi, what happened to this one? Okay, there are 900 people the company had surveyed. Okay, so let's use that one. So 900. So 900 minus 900 minus 398 minus 147 minus 142. The remaining number of people is 213. So this is outside, meaning to say what is the meaning of 213? Do not like either of these two animes. Oh, I guess I was wrong. Okay, 147 must do not like actions. Like action, both like. Okay, so meaning to say, sorry, these 213 do not like any of these two cartoons, anime. Okay, this 147 here like action, sci-fi, and fantasy, and this 142 likes fantasy only, 398 likes action, sci-fi. But the 213 here do not like any of these of those cartoon movies. Okay, so for the first question, the answer is, so letter A, like action but not sci-fi. Like action, sci-fi, where's that? But not fantasy. So the answer must be those people that like action, sci-fi, but not fantasy. This object here. Okay, so the answer is 398. Okay, so 398 people. Okay, for letter B, like fantasy but not action, sci-fi. So the answer for the second question is this one. No? Sorry. Sorry, I have to use a highlighter. Okay, the answer is 142. Okay, so these are the students that the people that like fantasy but not action, sci-fi. Okay, this one. Okay, let's wait again for the program to respond. Okay, the answer is 142 people. Okay, for letter C, do not like either of these types of cartoon movies. The answer is 213. Okay, outside. The answer is, what happened to letter C? Okay, this one. Okay, so for letter C, let's wait for the program again to respond. Okay, so letter C, we have 213 people. Okay, so that's the end of our lecture. So I hope that if you uh, are slow in studying, all you have to do is to repeat this lecture video for your own sake before taking the exam. Okay, so uh, just try to answer some of your exercises as, in the Google Classroom that I've posted, and then please study again and again until you comprehend all the things that discussed in this lecture video. Okay, but don't forget that you have to subscribe by clicking that uh, red button, the subscribe button, and the bell button down below. Okay, so thank you so much for watching. God bless everyone. Wait for the uh, chapter 3, okay, of for our another discussion. Just look at your outline course, the outline of this course. Okay, so thank you so much. God bless everyone. Thank you.